Alright, in this demonstration, we'll be showing you what happens when we drop a magnet, a strong neodymium magnet, through a copper tube. Now, we'll drop it without the copper tube. Whoa. It's much faster. In this experiment, we're seeing that when we drop the magnet, as the magnet enters the copper tube, we see it changes gravitational potential energy into kinetic motion. And that kinetic motion then creates a magnetic field which then opposes the descent of the magnet, and which we then see as the magnet falling slower than if it didn't have the copper tube around it. That's really interesting. So next we'll talk about what actually causes this to happen. So in this experiment, there are two main equations which describe what happened. We have Faraday's law of EMF induction and the magnetic force, which is from Lorenz's force law. So in the experiment, as our magnet approaches the copper tube, the EMF within the copper tube is zero. But then as the magnetic flux intersects the copper tube, we see a change in the magnetic flux over time, which then induces an EMF within the copper tube. So then, as it continues to fall, the current in the copper tube itself, which intersects with a magnetic field, then causes an opposing force, which decelerates the fall of the magnet through the tube. So if you look at the this diagram more closely, the magnetic field as it enters creates a magnetic field, and assuming that the magnet is in the north-south direction, the magnetic field lines will flow from north to south. This will then cause a current which will go at the north side of the magnet. There'll be a current which flows counterclockwise, and that current itself will then create a secondary magnetic field, which will run following the right-hand rule. So it'll flow clockwise. On the other hand, on the south side, the magnetic field, because the magnetic field is approaching this side, the magnetic flux is increasing, and so the current flows clockwise on the bottom half. This causes the magnetic field to flow in the opposite direction. So if we look at the top side, the magnetic field will be flowing in the same direction as the induced magnetic field will flow in the same direction as the magnetic field of the magnet itself, and cause and actually pull the magnet upwards. On the other side, on the south side, the induced magnetic field, which actually pushes away the magnet as it descends. So we see that as the magnet falls, the bottom side is pushing the magnet up, and the top is pulling the magnet up. In conclusion, this describes Faraday's law pretty well, and from the results of our experiment, we saw that compared to dropping the magnet without the copper tube, it was much faster than with the copper tube.